Okay, welcome to the second video on special relativity, this time looking at time dilation in a bit more detail. So we're looking at what is meant by time dilation and how to make calculations involving time dilation. And we'll mention why we don't experience time dilation in everyday life, or at least from our point of view anyway. So what is time dilation? So time dilation is the difference in a time interval as measured from a stationary observer's point of view and a moving observer's point of view. So it's the difference between the stationary and moving observer's reference frames. So it's often discussed about this particular example here. So if we imagine a ball and we're throwing up a ball, then the time that it takes to do that would be the distance h up and h down divided by the speed s in this particular case. Okay, so let's look at this from a different reference frame. So this is from the point of view of observer 2, who is watching this ball getting thrown up and down inside a moving train that is moving from left to right. When they look at that, they can see that the ball is following a path up to the top, path D, and then back down path D from that. And it's clear to see here that the distance the ball has traveled from this second observer's point of view is greater, and it's happening in the same time. So the two objects moving relative to each other, the point of view of each will be that the other's moving clock is ticking at a slower rate than the local clock. And that's because it must be ticking slower for it to travel a greater distance in the same time. The faster the relative velocity, the slower the time will appear to move. Okay, and we can work out how much the time is dilated. So t dash, the dilated time as observed by the stationary observer. T is the time that the observer on the moving object sees, and that seems the same to them, whatever the speed it's going at, and c is the speed of light. And so what we have is that t dash is equal to t divided by the square root of 1 minus the speed of the moving object, v squared, divided by c squared, the speed of light squared. And this is only really significant when we get to particularly large values of the speed. So if the speed v is really quite small, then the bottom term effectively becomes 1 minus 0, and the square root of 1 is 1, so the times are equal to each other. So let's look at the case where a rocket is going past Earth and it's traveling at a constant speed of 0.9 times the speed of light. So this is 90% of the speed of light. And the pilot on the rocket here measures that the journey takes 240 minutes. And we're asked to work out how long is it going to take from the point of view of an observer looking at this rocket that's traveling at 2.7 times 10 to the 8 meters per second. Okay, so what we're looking at is the time t as observed on the rocket is 240 minutes. We have the speed of light. We have 90% of the speed of light, which ends up being 2.7 times 10 to the 8. And if we substitute in those numbers, we can see that we end up with a dilated time of 550 minutes. So to the person in the rocket moving up very quickly, it appears to them that 240 minutes have elapsed. To the person observing the rocket, from their reference frame, it appears that 550 minutes have elapsed. Okay, it's possible to do the same calculation, and instead of substituting values for v squared and c squared, you can use 1 for the speed of light and 0.9 because it's 90% of the speed of light. Because effectively you have 0.9 times c and you've got 1 times c, and the c's are going to cancel here. So it just depends which one you prefer as to whether you just want to multiply your values or just substitute in the fractions that are there. So why don't we notice these differences in everyday life? Well, the reason is that we can't actually move fast enough for time dilation to have an effect in terms of what we notice. But that doesn't mean that it doesn't actually impact upon our everyday life. And indeed, if we didn't take into the effects of special relativity and time dilation, many of the things that we do use wouldn't actually work properly. So if we look at this particular graph here, this is of the Lorentz factor. Now this is the ratio of the square root of 1 minus v squared over c squared, and how it deviates. So it's really only 1, and it really only deviates significantly when we're at about 70% of the speed of light, 60 a little bit, but 60-70% and above is when it makes a significant effect, and it makes no difference when we're less than 10% of the speed of light. And so that's why we don't see anything taking place usually. So how do we know this is the case? Well, if we fly a very accurate clock on a plane, we can actually see that the time recorded for the clock on the plane is slightly slower than the time recorded on the ground. Our global positioning system, the GPS maps, they have to be corrected for time dilation effects. Other evidence is subatomic particles, muons, that are detected at the Earth's surface, even though they shouldn't be, because they should only exist for a short amount of time, but because they're going very fast, time dilates for them and runs slower, so we can actually detect them on the surface of the Earth. We'll have more details about these as well. So we have observed the effects of time dilation. We have flown clocks in planes, and we can show that they run more slowly when they are in the plane. Okay, there's a video here about an atomic clock being flown on the plane that you can watch about that. And also some about the how GPS works and the corrections for relativity because of that. If we didn't correct the time for our GPS satellites, then we would have our distances out by about 10 meters by the end of the day. Okay, finally a bit about a muon. So these are produced by interactions between the cosmic rays and the muons in the atmosphere traveling almost at the speed of light. When we measure them in the laboratory, they exist for only 2.2 microseconds, so 2.2 millionths of a second. And if we do distance is speed times time, this should mean that at that speed they can only travel 660 meters from where they are created in the upper atmosphere. But what we find is we can detect them on the surface of the Earth because of the effects of time dilation. So if we put in our speed there, and we square that and we divide it by the speed of light squared, and we take that away from 1 and square root that term, and we see that the 2.2 microseconds is changed into 84 microseconds from the reference frame of the stationary observer. And therefore, because the time is dilated to 84 microseconds, then the distance that they can travel in that time is 25 kilometers of distance. So we can detect them at the surface of the Earth when they've just been created in the upper atmosphere. Okay, here's a different example. How much slower would a clock need to be traveling on a spaceship at 2.8 times 10 to the 8 meters per second? So there's our time dilation formula, and we're going to substitute in our values. 2.8 times 10 to the 8 divided by 3 times 10 to the 8. We've cancelled the times 10 to the 8s there. You can do that or not do that, doesn't matter, as long as you remember to square the terms and take them away from 1 and square root them. These are the kind of calculations you often need to do a couple of times just to make sure that you've inputted the values correctly. And what we find there is that the time is dilated from 1 second to 2.78 seconds. So a stationary observer would see that it takes 2.78 seconds on his clock for each tick on the spaceship's clock. Okay, many of the effects of special relativity are weird, and you really kind of have to accept that they are weird and it is strange. And if you accept that, you can then make the calculations for the changes that are there. Okay, calculate the time that would pass on Earth if a year was passed on a spaceship traveling almost at the speed of light. Okay, so here we've simplified it again because we've got v squared divided by c squared, and the speed is almost that. So in our relationship, we can actually substitute v squared upon c squared as 99.9%, so 0.999, and we end up with 22.4 years for 1 Earth year. You don't have to do the calculation. It'd be quite acceptable for you to multiply that by 3 times 10 to the 8, square it, divide by 3 times 10 to the 8 squared, take away from 1, square rooted, etc. So you don't have to do the simplified notation here. Okay, so what have we talked about? We've talked about time dilation being the difference in time interval between a stationary and a moving observer, and we've made some calculations involving time dilation and said that we don't experience them in everyday life because the objects that we're moving in don't move more than 10% of the speed of light.